Our last speaker of this session is Bill
Spohn.
Spohn. Okay. So please present your paper.
Okay. Hey, Bill. Hi. I did bring a cheering section, right, Don? Thank you.
Well, you know I'm a big fan.
I guess
One of
so,
my favorite
yeah.
podcasts.
So, yeah, that's one of the reasons why I'm here. Don invited me. I do a podcast called Building HVAC Science, which is primarily for my customer groups, which are heating and air conditioning contractors and building performance. And there's this crossover between these two areas, and it's the shell, it's the enclosure. And there's a lot of ways with the building performance impacts what gets inside the building, and that includes things like soil gases and radon. So I wanted to give an overview of that. Originally, we were going to have Joe Medosh come. He's a very talented presentation creator, trainer. He works for the Hayward Score. My company is True Tech Tools. We sell the test and measurement products. We have a booth here, booth 23. And if you haven't entered our drawing yet, please enter the drawing because it's $350. I'd enter the drawing if I could. So I'm going to go through this presentation and talk about Building Science 101. Some of the building blocks of building science are realizing what we're trying to detect and analyze is heat, air, and moisture. Easiest way to remember it is HAM. It's the movement of heat, air, and moisture really lends towards the performance of the building, the energy, the performance, the indoor air quality, and the overall health of the building, durability. We'll be talking about air tightness of the enclosure, how some of the pressures are created, and I think I'm learning a lot just this last day or so about radon and vapor intrusion. And I think some people here may actually know a little bit more about this than I do, but I want to present what I know from my perspective. So if you see anything here that's kind of going off base, raise your hand, let me know, and we'll get it corrected. Some things are the cargo that comes along with this pressure and the penetrations are things like soil gases, moisture, loss of energy, and through these holes, literal holes, are bugs and pests. So house is a system, it's all connected. So this is really what building science is all about. One of the really easy things to understand is about moisture. Can I move that little?
Yeah, we should be able to drive that someplace.
Where do you want it? Just off in the corner, left or right? Down there, yeah.
Is this good?
That's
Oh,
good.
there is
Oh,
off.
great.
Oh, beautiful.
Perfect, thank you. Appreciate it. So if you allow this moisture to get inside the house, to find a way inside, it can cause problems with energy, with comfort, energy bills, more energy required for the air conditioning to operate, to dehumidify, and then get into the materials and deteriorate foundation, building materials, home materials, causing eventually some repairs. And a lot of this is due to the vapor, the excess humidity in the air coming into contact with a condensation surface, a surface that's below the dew point, and you don't always know where that surface is. It can be on your surface, or it could be a surface buried inside the materials of construction, or in a place like a crawl space where you never visit and you have no detection means down there. So getting this all under control is very important. So this is a picture of an average home, and we put holes in a home in order to use it. If it were just a perfect slabs of material, that would be great, but you really couldn't use it. It wouldn't be very functional, but it wouldn't be very comfortable to live in. So these holes are bridges to the outside. They're penetrations to the outside. They need to be sealed or controlled or understood. There's also holes inside the home. And this illustration will show you that there's holes running in between the floors, in between the walls, from subspaces to super spaces in the home. So all these controls, in order to make it functional, to make it livable, to make it comfortable, cause pathways. The other way to think about a home is that in addition to being Swiss cheese with all those holes and penetrations in it, it can also be a sponge. Materials can collect and accumulate in here. There's been a study that I've been involved with personally 4 times now, called ROCUS, Reduction of Outdoor Contaminants in Indoor Spaces, ROCIS.org. It's funded by an endowment by the Heinz Foundation. And what they've done is, this has happened in the Pittsburgh area where I live, they give individuals indoor air quality detectors for particulates, for radon, for carbon monoxide, and CO2, and you set them inside the house, and they collect the data and analyze how the outdoor data, particulates, et cetera, affects the indoor. So this is very much about this sponge effect. They're in about, I think, around the 50th consort of citizen scientists. People actually in the community get together and collect this data for 3 weeks. So it's very interesting. I would encourage you, if you're curious at all, look it up, ROCIS.org, rockus.org. And because we spend so much time inside the house, and this absorption of the materials, the collection, the concentration of these, the indoor air can often be worse than the outdoor air. So all these things that are outside, fire, smoke, pollutants, chemicals, pests, they can eventually make their way inside through air leakage pathways. And there's a thing called the blower door test, and everybody thinks that's an energy test. We have a blower door in our booth. It is an energy test because it talks about air leakage, but it's also a contaminant pathway. This is a new way to think about it, to really tie in the correlation between a healthy indoor environment and the outdoors. So all these different materials can come inside and collect inside the space. And if you have better ventilation, or you just simply open the windows and doors, you can move some of these contaminants out. In addition to things outside coming in, there's things that are inside that are produced by sort of the activities of daily living. Fire and smoke, if you're a bad cook. Carbon dioxide from exhalation. Particulate matter from dusting, from things being tracked in from outside. Even skin cells and just people create sources of indoor air contamination. They can be recirculated unless they're properly filtered or aired out. I'm not trying to paint a doom and gloom picture here, but just trying to give you an idea where some of the science is leading in terms of all these things being tied together. So one of the things we want to look at is, a lot of times we look at a lot of our measurements as being static, but there are dynamic forces at play, and we'll take a look at some of those on the house. So one defining principle we talked about before, heat, air, moisture. Heat always moves from hot to cold. So that's a form of drive which can impact, and again, people here are probably more sciencey than my typical presentation audience, and understand that you don't make something cold, you take away the heat from it. But when it comes to a house, this heat movement can also cause air movement. So in the wintertime, things are moving outside of the structure and can cause a stack effect to move through the pathways, those internal and external pathways, move air and whatever is within the air. And in the summertime, it can be the opposite direction for the heat moving towards the cold. And of course, there's also the force of wind pressure, and is illustrated here. Wind imposing upon a structure creates a positive pressure on one side, creates a negative pressure on the other side, as sort of like the wing effect or the Bernoulli principle. And in the summertime, that causes drive usually downwards from the attic spaces, if there's an attic, and in the wintertime upwards from the lower floors or the basement area, causing these drives from these internal Swiss cheese factors as well as us external ones. So this illustration here gives you a graphic on how the combination of the stack effect due to thermal and the wind can actually create quite complicated patterns of airflow and pressures which can drive vapors to move throughout the house. And can also do things like, you can see in the basement there's the mechanical system, there's a furnace. That could be in a gas-fired water heater that could cause depressurization of that space. And one of the things in building science is called combustion air zone measurement. So in as much as a lot of people here measure sub-slab pressures to understand what's going on in the pressure drive there, you can also have these pressure differentials created by the wind and stack effect and mechanical ventilation upset the operation of equipment and cause other indoor air quality issues. So there's cases where air sealing for insulation can or cannot be an air barrier. That first one in the upper left corner is foam board insulation that's been foamed in place, and that's insulation that is also an air barrier. That foam board is not going to transpire too much vapor through it. However, things like fiberglass insulation, you've probably seen this a lot if you've worked around houses or buildings, but it can actually look, sometimes it's called filter glass in the home performance industry. That may be the same in yours, but pipe penetrations, things like that, you have all those air streams moving through it and all the particulates in them accumulating over hours and hours and days and years. So there's something in the home performance industry called the pen test, the red pen test. I don't know if anyone here has ever heard of that. But basically you understand how a structure is built and you try to look at its plan, or you make a sketch of the plan, and then you trace around and make sure all your thermal barrier and your air barrier are all continuous. And this illustration here, it's sort of a nuance, but you can see if you have a duct system, an air handler in the attic, that the air barrier now is part of the air handler in the duct system. And if that's not well sealed, you've lost your air barrier. So you have the ability to either pull things in from that space where the air handler is, or cause a change in pressure, which can pull things in from other spaces. So the thing to keep in mind, this is the thermal barrier, and you try to do a pen test where you continuously walk around an illustration of the structure to make sure that everything is contiguous and you're missing no places where you're missing insulation and no places where you're missing the air barrier. And again, you're probably familiar with this, but wearing a nice insulating sweater doesn't cut it when there's air movement. Wearing something that has an air barrier with insulation feels a lot warmer on a cold, breezy day. And we're talking about all this air movement through the structure. So this is an illustration of the contaminant pathways, and the green air is the outdoor air, and we're going to walk through here and see how it can get in to the indoor area. So even though those penetrations are there for electrical wiring, for plumbing, maybe for chimneys or stacks or ventilation, there's also those tiny gaps between the wallboard and when the walls are installed. Those tiny gaps may look like nothing, but they can add up. Think of all the linear sheets of, in an average size home, there may be 50 to 60 sheets of drywall, and all these interfaces, if they're not sealed, they can be, if they lead to areas like this, they can be pathways of contaminants and vapors, and also just kind of that driving force from one place to another. So this is an example of some of the pathways that people discover all the time. I had them in my house, several houses I lived in, although recently we built a house where we really tried to get control over the air pathways. We can talk about that later, or come by my booth and we can talk about it. But you can see that transition there, moving from all the holes to actually foaming that and taking care of all the air gaps is going to make a tremendous difference in the energy and the air quality inside the structure there. So let's move around and take a look at the outdoor air getting into the interstitial spaces. So at first we're thinking, well, these interior walls don't make, they're all inside, so what does it make a difference? But if they have any kind of connection to an outdoor air area, they're gonna be pulling in and be in a pathway. And what would cause that air movement going from the second floor to the first floor? You see a large kitchen exhaust hood, which is depressurizing that space. And they can run up to 100, 200 CFM, and there's some stupor ones that run even 400, 500, 600 CFM. So that's pulling an awful lot of air through the structure, and air is going to take the path of least resistance and find a way to move through. So even though you're exhausting maybe the cooking odors from the kitchen, you could, if you don't have makeup air, it will find air somewhere else. And if that air is to a space that you didn't want it to come from, it's going to come from there anyway because the pathways are present. And now we'll move around and look at the sheathing. And this could be where the gaps in the sheathing and the band joist area, typically they're not sealed. More and more people are paying attention to that. Like I said, in our house, we taped and sealed every single joint we could to the exterior. We wanted a very continuous air barrier. We did the red pen test around our house. But typically you're not going to see that, and you're going to see areas where these can leak in. And again, we're looking at the kitchen, and we can see where that exhaust hood, when it's running, is going to be pulling from wherever it can, the path of least resistance. And we'll go around into the basement area and see again from that band joist area. And what could be the source of negative pressure that's pulling in to the basement area could be the clothes dryer. Again, 150 to 200 CFM. That could be causing a depressurization of that space and pulling in the air from the outside, which could affect comfort, energy consumption, as well as any kind of moisture issues. If it's summertime and you have a relatively cold basement, you have high humidity outside, you bring in high humidity air, and it comes into contact with something below the dew point for that air, and now you've got wetting of those materials. This is something very interesting, and the calculations here are done over about 3 to 4 months. So it isn't like this is instantaneous, but a sheet of gypsum board, and this is supported by buildingscience.com. If anyone's familiar with Joe Stebrick and the group up in Massachusetts, they have a lot of great articles, technical papers, references on building science. This is supported by from their research. If you take a sheet of drywall at 70 degrees Fahrenheit with 40% RH on the inside, and you have a northern climate, so you have the thermal drive making it go from hot to cold, moving outside, you get about a third of a quart of water. I guess it's a half to a third. During the course of about 3 to 4 months, say like the heating season, if you have a 1 square inch hole of air leakage, the amount is astonishing. 30 quarts of water could move through that hole due to the drive from the temperature difference and the moisture difference. So vapor diffusion has an effect and an impact, but air leakage has a huge impact. And I would say, if anyone here is from a northern climate and they feel like when the furnace kicks on, it gets dry inside the house, it's because it's making dry heat. It doesn't make dry heat. It heats the air. What is probably happening is you're pulling in air from outside at a very low absolute humidity that's coming into the house that's causing it to, through small gaps like this, causing it to drop the relative humidity and become dry. So it isn't that you need a humidifier, you need to seal the air leaks. That's usually the case. So in a mixed climate, this is to show The diffusion is the blue line is the sort of the humidity moving through, and this is just to illustrate the difference in the amount of total water vapor if you collected it as a liquid between that small hole and just diffusion through the material. If anyone else, another great resource that I use a lot is something called the Energy Vanguard website. Dr. Allison Bales from Georgia preaches a lot of good information there, a lot of short blog type articles on all kinds of aspects of building science and HVAC. And he's got some really good explanations about things like sealing attic hatches and things like that, pathways into the attic, especially in northern climates, where a very small hole can cause a terrific loss of thermal energy. He explains all the physics, not me. So this is, again, to give you an idea of the types of devices that we tend to have in our houses that can cause this depressurization and air movement. And if they're not balanced by some kind of supply, they're going to find their way through the cracks and crevices of the house, the interstitial spaces, and pull through that air. And the Joe Medosh kind of coined a phrase here, mechanical forces, the me can control forces. It's the things that we use for our kind of activities of living. They're things that are under our control. So it's especially important to be aware of those kind of things. Now we're going to do an illustration of a bath fan and a kitchen fan and give you an idea of the volume of air that can be pulled through when running for 20 minutes. So it's a 50 CFM bath fan times 20 minutes, 20 times 50 is 1,000 cubic feet of air, and a kitchen fan at 100 times 20 minutes is 2,000 CFM. So just to give you a visualization of how running these mechanical devices, if you let them run too long beyond their point of, of function, you can actually, start to affect the indoor climate, both from energy, comfort, and a health perspective. Now this is running a clothes dryer, which typically runs for quite a bit longer. So it's running 60 minutes at 200 CFM. That's 12,000 cubic feet. And just to give you an idea of how that can depressurize the structure and move in outdoor air. And the orange air is the indoor air that you had in there that was conditioned, and now you're pulling in the green air, which is the outdoor air, which was not conditioned, and now you have to spend energy conditioning that. And the answer to a lot of these things is understanding the mechanical forces and providing makeup air, either localized to the device or using things like, again, I'll talk about my house, we put in a heat pump clothes dryer. So it has no connection to the outside, and it functions very well. It doesn't make the laundry room hot or humid. It just uses a heat pump, and it takes the condensate out of the air and pumps it down the drain. So there are possibilities for doing things like this. Now we'll talk about moisture, and of course you understand rainfall, bulk moisture falling and getting into the soil next to a structure. And hopefully you've got the correct eaves and wind protection and cladding to stop bulk moisture from coming in directly. But then these pressures now can start to pull in the humidity and the moisture from outside. And then you get some wind drive on top of that, and you fill up a house with moisture. The illustration here shows If you look on the right half of the house, we have an attic that's been sealed up to the rafters, and versus an attic that does not have any air sealing so much in the top floor, and you're actually leaking out. The one on the right, which is air sealed, which you may think you've done a better job by air sealing it right up to the rafters and encapsulating the attic, can actually then trap in the moisture if it's not under control. Again, the house is a system. You got to think of all these things together. Understanding how things work and monitoring them is very important. So this is zooming in to show how, in this case, like a leaky top plate in the attic is actually working for you by exhaling that moisture versus trapping it in. Another thing to realize is if you look at the ceiling joists, the beams there, the ones that are exposed, you really do need to encapsulate fully around the beam, because the temperature difference of that material, if it's not insulated, is going to cause a point of condensation for any kind of moisture that gets in there during the heating season. So this is to show how supply, this is an air handler that's in the attic. It could be in the basement. It could be inside the crawl space. But the supply leakage, because the air's got to come from somewhere, it's going to be pulling, it's not pushing it all back in. The red arrow coming back in is only one arrow, but your air handler is moving 2 arrows worth. So it needs to pull it in from the outside. So supply leakage in a case like this can create a negative pressure inside the structure. And the duct leakage, the amount of duct leakage, that is the amount of the CFMs that aren't getting delivered to where they're supposed to be, averages between 12 and 40%. Actually, my business partner, he had a process done on his house that sealed the ducts from the inside. His were 57% before they did the sealing of the ducts. So it can be pretty bad. And a lot of times they're buried in the walls or in places they're hard to reach. And so this is return side leakage. This can cause a positive pressurization because the return is pulling, we'll just say 200 CFM, 100 from the space and 100 from outside because of a big leak. It's pushing 200 back in from the supply, so now it's created too much pressure inside. So this can force things out into the structure say in the heating season. If it's relatively, comfortable inside, 50% humidity, you're now going to be driving that 50% humidity air out through the interstitial spaces, perhaps hitting a surface which is below the dew point for that air and causing internal condensation, and there's an opportunity for mold growth and just degradation of the material. So blower door testing is a big step towards understanding the air leakage to outside. Is anyone here, everyone, who's not familiar with how a blower door works? Okay, sounds like looks like you all are. So blower door test basically depressurizes the structure, has a fan that's calibrated to remove a certain amount of air. It then has a sensor in it to tell how much air is moving through the fan. And what you're basically doing is trying to create a pressure inside that represents a test pressure of 50 pascals. I say blower door testing is best done at the time of construction, and by that I mean that's the best opportunity to make the repairs for air tightness at the time of construction or renovation. It becomes more and more difficult. We had a house that we moved into. It was 14 CFM 50 when we moved in. We did some repairs and got it down to about 11. Did another series of repairs and got it down to about 6, or excuse me, ACH 50. So 14 to 11 to 6. It really had to stop at 6 because it wasn't financially viable to try to find all those leaks. So a blower door kit, if you're, again, it sounds like you're familiar with it, but it's a fan, calibrated fan, a door cloth, a frame, hoses, and a meter that allows you to assess what the airflow is through the fan. And I've seen this done in a couple houses by friends of mine who are practitioners, but doing blower door guided air sealing, that's basically the best, one of the best ways you can do it, is you use the blower door to pull in the cold outdoor air, and then you walk around with the thermal imager to map out where the areas that are getting cold on the surfaces. That usually indicates that there's an air leakage behind them, helps you find that air pathway to outside. And I say take all right turns, that was just, I thought, very clever, because when you take pictures of the thermal imager, you often forget where you are, so you can kind of walk yourself back around through the structure. So the air changes per hour at 50 Pascal standard. You might be familiar with something called the passive house standard. There are a number of different points in the passive house standard, about half a dozen or so, but one of them is this air tightness or air leakage, 0.6 ACH 50. The 2009 IECC is at 7. The 2018 IECC is at 3 ACH 50, but many states, including the state that I live in, Pennsylvania, have decided to derate that to 5 air changes per hour, and that's the house, that's the blog site for the house that I built. We came in at 1. So it's a pretty good house, close to that passive house standard, but got a lot of the air leakage under control. Not everything, but got a lot of it under control. And you know, the goal, I think, for a lot of the work we do is about safety, saving lives, especially for radon and vapor intrusion. But there's also the sort of the corollary impact of making things more comfortable, reducing energy costs, and having better indoor air quality from the Swiss cheese and the sponges that we talked about initially. So sort of just in review here, the pressure and the thermal boundary should be continuous. That Penn test and in contact with each other is the best way to do it. Air carries the heat and moisture, which are some of the things you need to keep under control. Air leakage requires a hole and a pressure difference. That's what we showed with the gypsum there. Wind, heat, and fans, mechanical fans, can drive the pressure differences, along with leaks in the mechanical system can drive the pressure differences. Duct location and the condition of the ducts can cause room pressure imbalances. That gets a little bit more into detail with just where the ducts are laid out. And the blower door is one of the best tools to control this driving force and to quantify the air leakage. So Joe and I want to thank you for listening to this. Hopefully you got something out of it, and I'm open to any questions, but I hope I covered some things here. Dawn's hand shot up first.
Do you offer, like, teach any classes of blower door testing with thermal tracing?
And I leave that to others. So we're a good purveyor of the tools, but we can put you in touch with people that do have those resources. There's a good site, YouTube site called homeperformance.tv. It's Corbett and Grace Lunsford. They've done a lot of hundreds of videos on all different aspects of home performance, IEQ testing, taking part in studies and things like that. Another question?
Well, you talked about air tightening. What about getting some fresh air back into the house? What do you
Sure.
recommend?
Air, if you get below a certain point, I would say when you get around that 3 air changes per hour, you need to have dedicated mechanical ventilation. So there's exhaust only and supply only ventilation. I think that's dumb, because either if it's exhaust only, you don't know where it's coming from. If it's supply area only, you don't know where it's going to. It's going to find its way out. So balanced ventilation, I think, is the best way. That's what I put in my house, is an energy recovery ventilator So it actually has a fan that moves, two fans that move air into and out of the house through an exchanger, a heat exchanger.
And do you run that into your ductwork? Is that what you're doing?
I did it a little differently. I'm a little strange that way, but I did it. Mine is separately ducted. So I pull air from the bathrooms, the laundry room, and a closet area, and I push air from the ventilation into the bedrooms and the main living room, and my office, because I'm full of hot air. The podcast, you get it? It all ties together. But a lot of times, especially in retrofit situations, you do have to bring it into the existing ducting because you don't have that flexibility of installing new ducts. But I was building a new house, so on the blueprints it was separate ducts. Heating and cooling and ventilation are separate. My idea was bring in controlled ventilation air and then heat and cool it due to the loads expressed on the house from outside and inside. So it's almost more like a commercial dedicated outdoor air system that you would find, but done on a house scale.
And do you control it with CO, do you have any, how about controlling it with CO2 monitors?
Yeah, I won't mention the name, but there is a product out there that includes a CO2 sensor and a VOC sensor in it that you can program it to kick on. And I have mine set, once the aggregate house level gets to 800, it runs until it gets below 800. ppm
Use
CO2.
CO2 monitor?
Yeah, CO2, right. So that's the surrogate indicator of air quality that you use.
Yeah, and it'll actually turn it completely off if you get to 800?
Yeah, it will actually, what it does is it'll turn it off, and when it goes to turn on, it will actually look to see, it'll cycle the air in the house, not with the outside, but the inventor calls it redistributing the stores of fresh air. So if the spare bedrooms have fresh air because nobody's in them, let's take that fresh air and move it around the house and let's level it out. So it's very smart in terms of energy control. It isn't, bringing in more air to condition unless it needs to.
So do you have multiple CO monitors?
Now it's all central.
Just the central one?
Yeah, so.
Fascinating. Good.
I'm just curious, have you measured your home for radon?
Yes, and it's bad.
And it's what?
Bad,
It is.
yeah. So,
Lots of people here want to help you.
yeah.
Yeah, we know you.
So I'm in Pittsburgh, Pennsylvania. We did put in radon-resistant construction. That was the concept to first do that. So we do have a pipe, and it does go.
Passive system?
Yeah, it's a passive system, but it's not working well enough.
Yeah, have you made it active by putting a fan on?
Not yet. No.
Does it go through the roof?
It goes into a knee wall area outside the thermal and vapor boundary, and then through the roof. So there's an outdoor area.
I had $1 for everyone I saw that was terminated inside the attic space.
Yeah, no, not.
Years.
We had a good advisor on this one. So I think that's legit because it is technically outside, sitting in the knee wall area. And I even put an outlet on this side of the wall. So we can get
Similar
power.
wind turbine on top of that could help quite a bit.
Seriously?
Oh yeah, that's what I do with my passive systems.
Uh-huh.
Rather than rely on thermostat effect and wind and all of that, I put a wind turbine on top of mine. That way, you have a mechanically driven without electrical cost.
Got it. And I think there's also probably a way with this conditioning ERV, because there are two motors in it, I could offset it to put the house under positive pressure, slightly positive pressure to help that effect. So, thank you.
How about, a lot of homes now, they're insulating in the attic, like you showed, spraying foam or insulating in the attic. What's your vote on insulating the rafters versus insulating the floor of the attic?
I would defer to that Energy Vanguard website. He's much deeper into that, Allison Bales.
Okay.
And a lot of the blog post comments are really good because you're gonna get opposing views, and they all kind of they settle into different courts. But there's something I recall from one of his blog posts about a ping pong effect in terms of the using open cell foam. it actually absorbs the humidity and then it releases it later, and it keeps this humidity going back and forth in that space, which is bad.
Right.
Any more questions?
I got a comment.
What's that?
I said I got a comment.
Sure.
I would encourage any of you to listen to his podcast because he brings on a lot of the people he's talking about, and it helps you see things from different perspectives. And you'll learn a lot. It's really good.
Thank you.
So I
It's
enjoyed it.
called Building HVAC Science is the podcast.
Thank you, Phil.
Okay, thank you.